Hello, everyone. Good afternoon. This is Matt. I just wanted to do a quick mic check. If anyone out there can say, yeah, you can hear me. And then we'll get going in a minute or two, let other people filter in. Okay. Thank you. And we'll get going in a minute or two. Okay, we're going to go ahead and get going. It's just some housekeeping things. If you haven't been on a GoToWebinar before, there's an area usually on the right-hand side and there's a questions box that you can enter in the questions as you think of them, and then we can address them most likely at the end. We'll look at the questions and get them answered. Okay. And then if there's any other comments or anything, you can use the chat window. So, okay. Your hosts today are myself, Matt Jones, and also on the line is Pat Harrington. What we have prepared for you today is a short presentation on the Markforged Metal X 3D printing system. And from there, we're going to kick it over to Pat. He's going to go through an Eiger demo. Eiger is the software platform that runs the entire Metal X, actually all of Markforged 3D printers. Then we're going to come back to myself, and I got a webcam set up, and right now I'm right in front of the Metal X in our office here in East Aurora, New York, on this wonderful rainy day. So, and then we'll take a look. We'll use the webcam, kind of look at the equipment, and then we'll go on from there. So, Miller 3D, we're a reseller for Markforged and also 3D systems as well as Big Red. And we have a wide variety of different 3D printers, ranging from the general plastic all the way up through carbon fiber and, of course, metal. And this is not our only metal system. We also have laser powder bed as well. And we can do very small, fine little parts, you know, the range of a dime all the way up to over 40 inches. So we got a lot of different materials, a lot of technologies, and then also a lot of size ranges. But today we're going to talk about Markforged and what they're all about. And so Markforged, they started shipping machines in 2013. They're based up in Watertown, Massachusetts, which is just outside of Boston. And they started with a Mark I. It was a little small, little desktop FDM type of printer. And what was unique about that printer was the carbon fiber, the reinforced carbon fiber. And since then, they've been on a fast pace, track, and now today they have 6 different models of the carbon fiber 3D printers, as well as the metal platform, which is what we're going to look at today. So they're very in control of their entire platform. They manufacture all the hardware, which is the 3D printers, and also all the materials. It's actually pretty neat. If you get to go to their factory, you can see the onyx, which is the chopped carbon fiber. And they just have lines of these extruder machines pumping out that material. And then also the software. We call it Eiger. Eiger is the platform that will run any of the Markforged equipment. And you'll see just how easy it is when Pat does his demonstration of Eiger. So materials, we're talking about industrial materials. And really the mantra, the name of the game for Markforged is strong materials. They're not after the weak ABSs or the PLA materials. Their game is strong parts. So you see they have the plastics, which is the chopped carbon fiber, and then they have the continuous reinforced fiber in the middle there. And then, of course, to fit into the strong parts, they have metals. And so that's what we're going to introduce, the Markforged Metal technology. Now this was introduced, it was probably 3 years ago maybe. And, ever since then, they just been on a full court press with developing new materials. They introduced a larger sintering furnace, and really just honing in the software to have a better user experience and better results with the parts that you get out of the system. So basically, it did change the game. Pat and I, when we first started this division 6 years ago, we had a powder bed system in here for 4 years, and it was difficult. It was difficult to run. There was a lot going on in the laser system. So when this came out, we had it delivered, and in 1 week we had everything up and going and printing parts. So the safe part of it is that you don't need a explosion-proof room. All the metal powder is bound in a reel, and I'll show you the metal powder when we flip on the webcam. So it's safe. The actual 3D printer can work right in the office if you want it to. And then the sintering furnace and the wash is more, it needs to be vented outside. That's more in the industrial space, but it's all safe. Markforged really prides itself on making safe equipment. Affordable. The laser bed systems, as we know, they're $500,000 and up. So at about half the cost is the Metal X system with all the equipment included. So the barrier to entry was always not always the price, but a lot of times it's the price. And so when the Markforged Metal X came out, we started seeing the smaller to mid-sized companies really started to take a look at this technology. Easy. Like I said before, we had the system up and going in less than a week making parts. And you'll see the software that drives it is very easy as well. Really the caveat, the easy part, running the system is easy. And really where the skill comes in is designing your parts. Designing your parts more for additive manufacturing and more for the metal X system itself. So the metals, right now, available through Markforged and through Miller 3D, we have these 6 materials, which I think are very exciting, available right now. We actually, they're sitting right in front of me. We have a 17-4 stainless Inconel, H13 D2 A2 tool steels, and then also pure copper. It's not a copper blend, it's pure copper. In development is titanium and 316L, and this is not a short list. Their list is very, very long. And, you know, if you flash forward 5 years from now, there could be 100 metals. But there's one thing that's clear that Markforged does before they release anything to market, whether it be material, a new 3D printer, whatever, is they go through a lot of testing, a lot of third-party testing before they release it to market. So it takes some time, but when they release it to the market and to the users, they know it works. And in my mind, I'd rather that. I'd rather not be the guinea pig. So those are the next metals that are coming up, and we're definitely going to see more than these on this screen. So like I said, with the third-party testing, with each material that's released to the market, it also comes with a third-party verified data sheet. It goes through all the composition. It goes through the mechanical properties. In the case of copper, you also have electric and thermal conductivity that's important in that material. So all these are available, and if you'd like to see them, and it also has a little grain structure that you can see here that they get as well. So how does this work? So at the high level, you print it, you wash it or debind, and then you center it, and then you have your part. So it's a 3-step process. You print it, you wash it, and then you center it, as far as the physical part of what goes on. Iger and the software obviously comes before, and we'll take a look at that with Pat. So these are just some videos of what's, this is the 3D printing process. Obviously not this fast yet. It's important to know, though, what's going on here. And if you're familiar with FDM printing, which is I would say the most common, it works very similar. It's metal reel, a lot like the plastic reel. Heat it up and it's fed right through the nozzle, and you 3D print, just as you would in the plastic material. Also, the print head has a second nozzle, and that lays down this white material here. Now, the white material, what that is, it's a ceramic. So the ceramic is the interface between the actual part and the support structures. So this whole part will ride along into the debinds or the wash, and then it goes through the center. And then out of the center, this white ceramic material, it will turn to dust or powder. And then your part, it pops right off. So the supports are very nice to remove, and a lot easier if you're familiar with laser powder bed. I don't mean to keep hammering on powder bed. There's a very good technology, for certain applications. But as far as ease of use in your first time 3D printing, this is definitely the way to go. So then after you're done with the 3D printing, you open up the doors. It is a heated environment. You see the build sheet that it prints the part on. And then you just peel away the part off the build sheet, and you're able to use the build sheet again for another part. The build sheet is held down with a vacuum table inside the machine. So there's a vacuum table. You don't need air to the machine. There's an onboard compressor. And there's your part. So this is in the green state, what we call the green state. So the green state, if you look down under a microscope way, way small, you're going to see something that looks like this. These are the metal powder particles. And there's millions of them. And they're all held together with a wax polymer. So the wax is in orange, and then the polymer is in blue. So it's all holding the metal particles together. So now, the trick is, how do we get that all out of there? How do we get the wax and the polymer out of the green part so we're only left with metal? And this is where, remember when I said this is a three-step process? This is where the other two processes come in. So the next is a wash tank or debind. This is a way to get rid of the wax. So there's a chemical in there. It's almost like an industrial degreaser, and the solution, it basically permeates the part and extracts all the wax out of the part. So you can see you can do multiple parts at once. You can have different layers if you want, and you can't overwash a part, so you can leave them in over the weekend, and then once a part is ready, you take it out of the basket, and then you put it over into the drying area over here. So this is just drying and, making sure the part is at a certain weight. And there's a weight reduction that we're looking for from the printer out of the debind tank. That weight is the wax. And once we're good on the weight, then we can move on over to the sintering. So the sintering has a ceramic plate that you place the brown part. Now we're calling it the brown part after the wash. And this is the sintering furnace here. It's a tubular furnace. And you place your ceramic plate all the way in. There's a stop. And then I just noticed in this video you forgot one step, but that's okay. And then you tighten it up, and then you center it. Each of the materials has a preset centering curve, where it heats it up at a certain temperature, and then it'll heat it up, to around 80% of the melting temperature, and then the ramp down. And so all the materials are already set for you, which is nice. You don't have to play around with any of the heat curves or anything like that. And you can center as many parts inside the furnace as you can fit on the ceramic plate. And it could be small, it could be larger, it could be a lot of small parts. It doesn't matter. It's a fixed cycle, and each of the materials has its own cycle. So when you're done, you pop open the door, and right out of the furnace, it's completely safe. There's the sintering furnace is tricked out with all these different sensors and everything. So when you open up of the door, you're assured that it's completely safe. And now this part is 100% metal. There's no debind in there. There's no wax or polymer inside that part. It's 100% metal. Now you might have saw how easy it was to take the part off of that. We call this a raft, and this is the support system here. It's not that easy. So we typically we clamp it in a vise and just give it a couple taps on the back of the rasp, and then it pops right off. You know, in some cases, and like holes and things like that, they do just pull out very easily. Other times with a lot of surface area, you might have to give it a couple whacks with like a dud blow or something like that. So you might have noticed that that was a pretty small furnace, and it's, you know, very good for like sizes about the size of your fist or smaller. And Markforged has had this plan, you know, the whole time, is to build a larger center, and that's what they did. And it is out in the field and in the market, and it's nice. So now we have a larger tubular furnace, and we're able to either have one center plate for larger parts, or you can have a double stack here. And what this will allow you to do is have more throughput for the smaller parts, because it doesn't matter how many parts you fit on the center plate. In the center, it's all one cycle. So I just wanted to talk about one of our customers that before we go over to Pat. And the name of the company is Caldwell, and what they make is high-end window closures, door closures for all different companies, you know, large houses, you know, things like that. And they started off on this journey with just a plastic printer in mind. And what they ended up getting was a carbon fiber printer as well as the metal system. And what I find interesting is that they really adopted it. You can see right from the president, you know, it's part of their culture now, and they really can't live without it. So much so that they've ordered many more of the carbon fiber 3D printers, and they put it, you know, these printers at different divisions around the country. And it really allows the tool makers and the design engineers really to get creative, have design iterations, print actual functional tooling for production, and it's really across the board. So this is a video I'm going to play right now. I don't know if you can hear it over your computer. I can hear it on my phone, but we'll take a look here.
To make everything from prototype all the way through low volume production. That's 2 days.
Okay, I'm going to pause it right there, only because I think the sound was messed up, and I'll have to figure that out in the next go webinar. Sorry about that. That video is very good. If you have YouTube, just or go out to Google and say Markforged Caldwell, and then the YouTube video comes right up. We'll get that figured out for the next time. So we have 2 things left. We'll kick it over to Pat. So we don't only sell the machines. We also support everyone with our design for additive manufacturing courses. And this could be if you're on the early on stages of looking at 3D printing. We have a lot of different courses here. We got the fundamentals, we got the plastics, the metals, the business owner, and we could design a course that's tailored to you. And we did this, later last year, and we went on site at a company, and that worked out well. And also, Markforged has it covered on the back end. Once you actually have the equipment in house. You can either go to Markforged or they can come to you and they can teach you all about additive design for the Markforged equipment specifically. So with that, Pat, I'm going to kick it over to you, and we'll get the Eiger going.
Okay. Thanks, Matt. I'll just take the screen back here. All right. Are you able to see my screen, Matt?
Yeah, I can see it.
Okay, thanks. So yeah, as Matt mentioned, I'm going to take you through a quick overview of the Markforged Eiger software. This is the software that they use to run both of their metal and their composite systems. So just like any other 3D printing slicing software, it's going to take an STL file. So any 3D CAD software that you have is going to be able to save one of those out. And what we'll do is we'll start off with a file that you saw in some of those videos there. This is a mini motor mount bracket that's printed in 17.4 stainless steel. So we have here our grid pattern. This is the size of a part that we're able to print on our Metal X system. And then we have a few options that we can play with. So material, we can choose from 17.4 stainless, 3 different tool steels, an Inconel, and a copper. And then you'll see below here that we're also able to choose which type of sintering furnace that we're going to use to accommodate these parts. And what this really does is it dictates the size of the part that you can send through the whole process. So if you have a Sinter 1, you're constrained to smaller size parts, and if you have a Sinter 2, you're able to do, for the most part, up to the full build envelope of the printer, which you're seeing here. So I have a graphic pulled up here that kind of shows what size parts each of the configurations can accommodate. So here is the Sinter 1 on the right here, and these are your final part dimensions. And then we have the 2 different Sinter 2 configurations that we can do, which is a lower setter plate for taller parts. You can see the Z heights are higher here, or the stack configuration, which is great for higher volume of medium to small parts. And it gives you the dimensions of parts that can fit both on that top and bottom rack. Okay. So in terms of setting up your print, as Matt said, it's very easy to just choose some simple options and set this going, where compared to the powder bed system that we had in the past, with that system we were really turning and tweaking laser speeds and laser power and scanning speeds and all these things, where this machine's really just tell it how you want it to print and it will take care of the rest. So part orientation is very simple. In a case where this part maybe came in, maybe you designed it on a different plane system, came in like that, you're just going to go ahead and click on the surface that you'd like to be down facing, and it will automatically snap to that. So I'm going to spin that around here. And we can go into the settings tab. So we have some opportunities here to choose different layer heights. This is post-centered layer height. So what the reason why it's saying post-centered layer height is because these parts are actually going to be printed at a factor of around 20% larger than you design them in your CAD. And there's nothing you need to do in terms of compensating your parts. The software is intelligent enough to handle that on its own. So I'll kind of show you the difference here. If I switch over to our composite machine, this is the true size of the part that will be your finished product after it's sent through the whole process. And then this scaled up version is the scale at which it will print to accommodate for that shrink factor. Okay, so 5 thou is the equivalent of 0.125 microns, or 0.125 millimeters, excuse me, and that will be your post-centered layer height. Now, we also have an option in some of the materials to experiment with an alpha print setting. So alpha is just another way of saying it's an experimental print setting, something that they like to release to customers to give them an option to play with before they release it as a full finished print setting. But we've had some nice success with it. 50 micron layer height, that's the equivalent of 2 thou. So we've had good success with printing some parts with threads that come out quite nice. That's just another option that you have to choose to play with. Let's talk about some of these other options that they've made available. Centering stability is one that they came out with. If you think about when we're printing thin walls, so what do I mean by a thin wall? Maybe less than 2 millimeters, talking about that. The way that this machine prints is it's laying down a bead from a nozzle. Now the diameter, the ID diameter of our nozzle is 1/4 of a millimeter. So if you have a thin wall that is not an even multiple of 1/4 of a millimeter, what you would run into with the setting turned off is you're going to have gaps in between the beads that you place. And when those gaps get centered, it's not going to bode well for the structural integrity of the part. So with the setting turned on, the software is smart enough to take those gaps in between the beads and actually fill it in with fully solid materials so that you can be sure when this part goes through sintering, you're not going to have air gaps in your thin walls that will lead to strength issues going forward. We also have some opportunities to play with different support structures. So on this part, I'll show you the default support structure, and then I can pull up another part that goes into some of these alpha or experimental support structures here. Lastly, an option here is disabling the raft. So as you saw in the video, this part is printed on a raft. There is an option to disable rafts for smaller parts, or more flat parts, I guess, rather. But what we've found is the raft does quite a bit for making sure that the part shrinks uniformly in the sintering process. These parts shrink around their geometrical centroid, so the raft ensures that, in a part like this, you won't get uneven shrinkage in this smaller leg of the part versus this longer leg. The raft keeps the whole part kind of together so that it'll shrink more uniformly. But in certain parts and geometries, you can turn off that raft and save some material and print time. Lastly, we have the option to play with our fill pattern. So on these metal parts, by default, you're going to be printing it with a triangular fill pattern. And what that does is it actually saves you print time, quite a bit of print time. It saves you material, so cost. And then it also saves you quite a bit of time in washing, which Matt touched on. The time it takes to wash a part is really a function of how long it's going to take that solvent chemical to penetrate through the entire cross-section of the part. So with your part being infilled, that will take roughly around 12 hours for most parts. You can see that highlighted over here. But as we go towards solid, it's going to increase the amount of time that wash cycle will take. Another options that we have to play with are roof and floor layers as well as wall layers. So what you're seeing here on the side is it's telling us what that thickness is on the outside shell of our part before our infill starts. So this is particularly relevant for folks that want to print a hole, but it's a critical dimension and they really want to get in there and ream it out to get it perfectly to size. This will give them a little bit extra stock on the inside of the part that they can remove to get the hole to be true to size. And you can kind of control based on what we select here, how much post-centered stock is on the part before the infill starts. So those are some of the options here. If we go to our internal view, you can get a better look at the raft that we mentioned. And then if I go to my 2D view, you're also going to be able to see, as I scrub through the individual layers here, you'll be able to see this orange, which is the ceramic release material. And as I move through the part, you'll see the ceramic release material is added as this part grows on top of the support structure. And at the end of the sintering process, as Matt mentioned, we like to toss this raft, clamp the raft part in the table vise, tap the back of it with a hammer, and the part will pop right off of the actual raft. So pretty simple in terms of options that you need to designate for your parts. Let me show you another part here, just to give you an example of the options that they're continuously adding to this cloud-based software. And because it's cloud-based, you don't have to worry about downloading them. It's just you're gonna log on one day and see that, hey, you have new options that you can experiment with. So when we first got this machine, a geometry like this was very challenging, and basically we couldn't do it without getting creative with mechanically removing supports with maybe a Dremel or something. And the reason for that is the support material is going to be required underneath this upper flange, and it's going to connect the upper and lower flange. It's basically going to be a complete donut shape of supports around this inside neck, and there's no way to remove that donut shape. So that's why Markforged came up with an experimental print setting that we've had a lot of great success with in parts of similar geometry, which is Radial Separations. And this allows you to designate how many radial cuts you'd like to implement into the part. And if I go into the internal view here and I take a cross section, you can actually see here's my inside neck of the part. This is about halfway up the part. And here are the supports. And you can see these nice radial cuts in here. So this is going to allow this previously a donut support structure to be removed in 5 sections. We can also get creative with adding separations vertically in addition to horizontally. So by doing that, we'll go back to a layer, and we'll just say on this layer, insert a layer of ceramic release material. So you can designate where you'd like the printer to print this ceramic release material, and after the sintering process, on this layer, that ceramic release material will turn to a powder, and you'll be able to remove this support structure as 10 individual pieces rather than 5, because these 5 sections will break up into top and bottom sections. So it'll just make removal even easier. This is a great tool for parts that have more complex support strategies. Let's take a look at our metal printer in Eiger. So Matt's going to show you some of the parts that are going on it right now, but we also have the ability to tap into a camera, and we can kind of see what's going on there. Let's see if I can find some heat sinks. So here's some copper parts, and every 5 layers, it's going to take an image as it's growing our metal parts. And, sometimes we like to check in on our phone, make sure the parts are looking good. And you can do that right in the Eiger software. Another part of the metal process, which is captured in the Eiger software, is this wash tab. So as Matt mentioned, we like to wash our parts prior to sintering. It takes it from a green part to a brown part. And what we're really looking for to tell ourselves, okay, this part is okay to sinter, is the mass reduction. So Eiger makes that fairly easy. Let's take this same sample part, the motor mount bracket, and we'll click that we're going to wash this part. So it's going to ask us, okay, before you wash it, please record the mass of that part. So we'll say it's at 57.56 grams. And then it's going to start a 12-hour timer. As Matt mentioned, you can't overwash your part, so feel free to leave it in there for extra time. And then you will get an email from Eiger when your part has been in the wash for 12 hours. You'll go ahead and select, we're going to dry that part. And it will start another timer of 4 hours. We found that 4 hours is pretty conservative. It's more for larger parts. A smaller part like this, you can typically have your part dry within an hour or so. You just want to make sure all that solvent's evaporated so that when you take the next mass measurement, you're not measuring the solvent. So we'll say, okay, that part's dry. And then you'll enter in the final mass after you weigh the part, and the software will either not say anything, which means it's safe to sinter, or it will say, hey, your part has not reached the desired mass loss yet. Please rewash your part until we've hit the 4.1%, which is specific to a few materials, and in this case, 17.4 stainless. So let me pull up a flow chart that we have. Here are the mass reduction percents that we're shooting for in different materials. So for 17.4, H13, and A2, we're all at 4.1. Inconel is 3.8. D2 is at 4, and then copper is only 2.7. There's not quite as much wax in the copper material. As long as you get the okay from Eiger, you can put your parts into the furnace. The sintering process is controlled on the unit itself, but it can be monitored from Eiger. The run duration is really just a function of the material that you're running. It's not governed by how many parts you have in the furnace. It's just a function of what material you're running, so it's always better to load up the furnace with as many parts as you can to keep your per part cost down. And then those runs can be monitored from Eiger software. So if we look at this part here, this is a 17.4 run we did. It's going to estimate how much gas usage, inert gas we used, as well as our forming gas that are used in this process. All right, so that's what I had for you on the software side. Quick overview of the whole workflow there. Anything you wanted me to add, Matt?
No, I don't think so. We'll go on to the thanks, Matt. Yeah, it was good. Now, I flipped on the webcam. This is a live webcam. You can see my hand there. Just let me know if you can't see it. So basically, this is our Metal X, okay, and then we'll go down the line here. So this is our Metal X printer, and I'll show you where the materials are. The materials are up in here, and you can see we have one reel of the 17.4 on the left, and then the ceramic on the right. What's really cool about this is that I could go from 17.4 over to A2 in a matter of about 10 minutes. You can see this is the material. It's in a real form. So going from copper over to D2, A2, Inconel, whatever, I could do that relatively quickly. And really, by the way, A2 and D2 can't be laser sintered as well. Those are true tool seals like H13, and if I loosen this up, you can see the materials down here. These are actually some parts here, like this is the motor mount that Pat was looking at on the rack. So what we would do here is just, put in a vise, give it a little tap, and it'll pop up. This is an Inconel turbine blade right here. And if you zoom in really close here, you can see the 625 marker on the part itself. Then as Pat, mentioned, we also do copper. These are some copper parts that we did here. And then this is the honeycomb on the inside of the part, a little triangular view here. So that's the printer. We kind of march down the line here in my little cart. We have the centering furnace. And it's the same idea as what you saw in the video. Here's the readout. This is the radiation shield, basically like a heat blocker there. And then inside is the ceramic plate that all the green parts would go on. Okay. So this furnace is hooked up to this gas panel. And the gas panel controls the inert gas as well as the mixing gas. There's two types of gases that you use with the system. And one of the inert gas is all high purity argon, and that's to purge the inside of the centering furnace. The mixed gas is mostly argon with a small percentage of hydrogen. And that's just to make sure there's absolutely no moisture inside this centering furnace, because we don't want any corrosion or anything like that. Okay. And then lastly but not least, here's our wash tank here, or debine tank. And again, this is the basket here, so you put as many parts as you can fit in the basket here, and just let it run. This is really designed to be hands-off. The entire system is designed to be hands-off. And I can wheel it back here to give you kind of like an overview of the entire system. So that's what you'd be looking at as far as the floor space goes for the system. Now, as far as the gas tanks, you can see our argon gas tanks over here. We chose the actual gas cylinders. So I think 4 of those are mixed gas and the rest are the inert. You could also choose liquid argon as well. It's a little bit cheaper. It'll be like a dewar of argon next to the machine. The only thing we didn't like about the liquid argon is that it off gases if you're not continuously using it for the furnace. And so we're printing off and on, and so it makes more sense, to save the off gassing and go with the regular gas. So that, in a nutshell, is the system. Is there any questions on anything that you heard today? So again, we got the printing, washing, in the sintering. Okay, going once, going twice.
Oh, we have one question, Matt. It's do all parts wash for 12 hours? So for that question, it's really a function of the size of the part as well as the cross-sectional area of the part. So the answer is no, not all parts wash within 12 hours. I will say that a large majority of them do, of the parts that we've done. But anytime you're getting into larger parts, maybe that would bode for the center 2, or if they're solid parts, they will likely take maybe a day to 2 days to wash. And typically for those types of parts, we'll just leave them in over the weekend, and they tend to be ready first thing Monday morning.
Okay, there's another question. Is there a wash 2? Or wait a minute. Oh, okay, got it. So how many of the ceramic plates fit in there? So we have the smaller centering furnace, and so it's just one plate will fit in the centering furnace. Now, on a larger centering furnace, it's a lot wider diameter, bigger diameter, so the plates are bigger, and then you can stack 2 plates on top of each other. And I know some customers are even going to do three plates, but it will come with 2 plates. And then, is there a wash 2? No, it's just a wash 1.
But the wash one will be able to handle any size part that you could sinter. So size-wise, the wash one will be able to handle it. And then what we're seeing is, batch post-processing is very easy with this wash. You just put all of your parts in there. We've even seen people use, secondary baskets or racks in their wash so that they can stack parts.
So what is the envelope that
let me share my screen again here. I see another question from Harvey that says, "What is the range of part size this unit can handle?" And then I'll pull up the envelope of the printer itself. So hopefully you can see my screen here. And right now on the center 1, your part size you're looking at is 9 1/4 inches in the X direction by 2.69 in the Y. And then your height of your part is a function of whether it can fit within the radius of the tube. So if it can fit within that radius, it can go up to 3.19 inches. If it can't, it'll be 2.72 inches, and these are center 1 values. These numbers account for the scaling up factor. So these are your final as designed part dimensions. And then it will also account for that raft that's implemented to control the shrinkage. So after both of those 2 things, these are your center 1 part sizes. For center 2, on a single setter plate, you're at 9 1/4 by 4.85. And then again, if you can fit within the radius or not, 6.37 inches or 5.56 inches. With a stacked setter plate, you can see here's the lower. So we have the 9 1/4 inches is pretty consistent through all the systems in the X-axis. And then this will decide what your Y dimension and Z. And then on the top of that stacked setter plate, you can get some wider parts. So 9 1/4 by 7.15, as long as you can fit your Z within these 2 values. Let me pull up the spec sheet for the actual printer to show you guys how big of a part that you can print. But just keep in mind that it's got to be able to fit within one of those envelopes on the sintering for it to go through the process. Where did I put those? So right here under build volume would be the size of your envelope. But keep in mind, you have to factor in the 20% scaling factor. So really what you would really want to look at is this max part size, which accounts for that down here.
Okay, thank you, Pat. Okay, we're just about out of time here. Thank you for everyone's time. I really appreciate you guys hopping on here and listening to us and seeing what the Metal X is all about. If you have any further questions, reach out to us. You can email or call. And then, just as a preview, we're going to have another one of these next week for the metal. And then also on Monday, we're going to have a high precision plastics for production. And it's a really cool machine. It's called the Figure 4. And it's really dubbed as the digital injection molding machine. And we'll leave it at that. And okay, thank you for your time. Thanks, Pat, and hope everyone stays safe.
Thanks, everyone.